Here's a concrete example of how a classical network and a quantum network work together. In this slide, and in fact in the rest of the seminar, I will focus mainly on the quantum secure communications use case because that's the most mature application for quantum networks. I could draw similar diagrams for clustered and distributed quantum computing and sensing. In this diagram, at the top in blue, we have the classical network. There are two parties that want to exchange encrypted data over this classical network. There are many companies, including companies like Cisco or Juniper or Ciano or Fortinet, that offer the hardware encryptor devices that do the encryption at various layers in the classical stack. The bulk encryption of the data can take place at multiple gigabits or even terabits per second, and they use symmetrical encryption protocols, typically the Advanced Encryption Standard, or AES. These symmetric encryption protocols need both parties to agree on a session encryption key. In today's networks, this is typically implemented using asymmetrical encryption protocols such as RSA Diffie-Hellman or elliptic curve Diffie-Hellman. These existing key establishment protocols are expected to be broken by quantum computers due to the discovery of Shor's algorithm. These broken algorithms need to be replaced by a new key establishment protocol which is safe against attack by quantum computers. And this is what we mean when we use terms like quantum secure communications or post-quantum security or post-quantum cryptography. There are multiple ways to do this, but one possible way to implement quantum secure key establishment is to use a quantum network. And in this diagram, the quantum network is shown in red at the bottom of this slide. The quantum network uses the special properties of quantum physics to enable the establishment of an encryption key between two parties in a secure manner. I'm not going to get into the nitty-gritty details of how this works, but the basic principle is that the laws of quantum physics are leveraged to make sure that any attempt to steal the key is guaranteed to be detected. And that's why often the term physics-based security is sometimes used to describe this approach. Now, there are two important things to notice about this diagram. The first observation is that the quantum network is not responsible for the high-speed bulk data encryption at multiple gigabits per second. The high-speed encryption still happens on the classical, on the blue side of this network. The quantum network, the red part, is only responsible for producing the encryption keys. The quantum network is more than fast enough to produce the necessary encryption keys, even if you roll over the keys very frequently. The quantum network hands over the encryption keys to the classical encryptor using a well-defined interface that I will discuss in much more detail a little bit later. The second observation to take away from this slide is that the quantum network does not replace the classical network. You do not need to do a forklift upgrade of your classical network. The quantum network only augments the classical network to offload one specific function, which in this case is the establishment of encryption keys.